Hey Royals, in today's lesson we're going to look at acoustic resonance in air columns. And this is how things like our trumpets or saxophones or trombones work. And before we get too far into this lesson, I want to demonstrate something to you. So I have here a tuning fork, and this tuning fork has a frequency of 256 hertz. And when I strike it with the hammer, you should notice that you hear it ringing at that specific frequency. So here we go. Right? However, if I take that tuning fork at 256 hertz and I attach it to a box, and this box has a fixed end at one end and it's open at the other end, and it's a certain length here. And on top of it is that tuning fork. And if I strike the tuning fork, you should notice something. Now, what I'm hoping that you're picking up through the speakers is that when it's attached to this box, it is much, much louder. And the reason for that is superposition of waves or standing waves. So let's go ahead and add that to our page here. We'll say superposition of waves, or we can call that a standing wave. It creates standing waves. Now, let's consider this box with its fixed end being like a spring or a string that has its end that's fixed as well. So as the waves come into it and reach the end, they're going to invert and come back. So if a crest was meeting the end of the box, it would invert into a trough and it would work its way back out of the box. Now, because sound is that longitudinal wave and it deals with rarefactions and compressions, it's hard to draw it. And so for our discussions, we're going to use these transverse waves where we can actually see antinodes and nodes. And for this wave to be amplified the way that it was on the box, we need that we have an antinode at the open end of this box. And at the end of the box here where it's fixed, we need to have a node. And to visualize this, let's draw it on our page here. So we have that our wave that comes in, let's draw it on the top half here. It's coming in and it's going to strike right at the end, forming a node. And that node is going to be reflected back. And so this is a wave that's on the top half of our box. It's going to be reflected back as a wave on the bottom half. And we get an antinode coming back out of the box. And this is causing us to hear it much louder because we're hearing the superposition of these two waves interacting with each other. So I get that the amplitudes will add together and it becomes much louder. And this can be demonstrated with a pop bottle organ. So I have one here. It's just a glass jar that has a cap that you can take off. And in it, there is some water. So hopefully you can see the water there. And it's at a level that's about 2/3 of the way up. And so if I blow into it, we should hear something. Right? And so if I pour a little bit of my water out, what do you expect to happen? Well, let's find out. The frequency's gone down. Now, if I pour a little bit more out, we should expect that the frequency goes down as well. Right? So this will continue to happen until the bottle is completely empty, and then you get the lowest frequency available with this bottle. So here we go with the lowest one. Right? So we can see this on the demonstration in front of us. So if we wanted this to happen, we have to have an antinode occurring at the top of our bottle. And so at the very bottom of the bottle, we have to have a node. And the lowest frequency that could possibly fit in this would be one that comes down from the antinode right into that node. And it reflects back as that antinode coming back out. Now, if we continue this, when we have a little bit of water in it, the length of that wave, so as it comes in, you can see that the wavelength is actually getting shorter. So this quarter of the wavelength that made it to the very bottom of our bottle is shorter than it was in our first picture. And so it will reflect back and give us that antinode at the very top of our bottle here. Now, if we continue one more time, we have the first incident node coming, or wave coming in, and it gets reflected back as that antinode coming back out, and you notice that the wavelength is again smaller. So the first one here has the longest wavelength. This one here has the shortest wavelength. And we know that wavelength and frequency are inversely related to each other. So if we have a long wavelength, like the wave on the left-hand side of our page right now, then the frequency is small. And the small frequency will cause a low or a lower pitch. So it will sound to our ear like a much lower noise. Okay, and then the ones with the shorter wavelength causes the frequency to be high, and that will cause a high pitch sound. Now, to summarize, what we just found with this pop bottle organ was that as the length of the air column got shorter, what happened to our wavelength? Well, the wavelength decreased. And this decrease in wavelength caused a higher pitched sound. Okay, so what happens if we wanted to keep the frequency constant, but just change the length of our air column? Could we get standing waves occurring? And the answer is yes, but only at specific lengths of the air column. And so remember, when we have this air column, we need an antinode to occur at the mouth of the air column, or the open part of the air column. And we need a node to occur at the closed end of our air column. So if the water was at this level here, we need a node right at the very bottom of that open space. And so as the wave comes in, we get this as its first fundamental frequency. And so the length of that is actually 1/4 the wavelength. And so if we compare this side of our wave, so the incident wave, to our wave here on the left-hand side, you can see that it is just simply the first quarter of that wavelength. So in order to have a resonance at a certain frequency, it's going to occur when the length of our air column is 1/4 of the wavelength. Now, if that is true, and we draw this dot all the way across, onto our second column, we still need to have a node here because the wavelength or the frequency is not going to change on us. So we still need this first wave being 1/4 of the way down to this location. But what happens is that we need it to still be a node at the very bottom. So this node here has to go to an antinode and back to a node. And I'll draw a pink reflected wave coming back, and here it is creating an antinode on the way back. Now, what is the length of this air column? Well, it was 1/4 of the wavelength for the first little bit, and then we added a half wavelength here. So I came down to the next one, the next antinode, so I added a half wavelength. So this length here is lambda by 2. So the length of this air column is going to be L, equal to 1/4 plus a half. So that's 3/4 the wavelength. Now the next one, we still need that node to occur at this location because the frequency is not changing on us. So the location of nodes is not going to change on us. And we need a node to occur at this location as well. So tracing in the wave that we already have, if we increase the length, I need a node to occur at the very bottom still to create this standing wave that's never going to change on us. So I have that it's going to come down and it's going to create a node at the very bottom. Now let's draw the reflected wave back. So it's going to go back into that node, the antinode, and then come back out as our antinode. So what's the length here? Well, I've added yet another half wavelength because I've come to the next antinode. So I've come up to this location here. In comparison, this is 1 full wavelength at that location. So I've actually gone a quarter of lambda plus that half of lambda plus another half lambda. So the full length of that error column is 5/4 lambda. So you'll notice here that I have a standing wave occur when the length is a quarter the wavelength, 3/4 the wavelength, and 5/4 the wavelength. So I'm going to show you a simulation that demonstrates this exact point. So in this simulation, we have just waves entering this tube, and this tube is closed at one end, as you can see with the grayed outside. And if I run this, you'll notice that the standing wave does not stay constant at all, because the length of the tube is not one of these resonant lengths. But if we take it down to, the wavelength here is 2. So we said that the first one occurred at quarter of the wavelength. So that would be the length being a half. So if we run it exactly at the length of our tube being half a meter, we run it, you'll notice that we get, yes, an antinode occurring right at the opening of our tube. Now, if I increase the length of that tube, you'll see that the superposition of these waves gets to a point where they meet up exactly again. And this is exactly at 1.5 meters. So if we run it at 1.5 meters, you see again, we get a standing wave occurring here. And that corresponds to 3/4 or 0.75 lambda. So the length of our tube is 0.75 lambda. If I increase this a little bit more, let's go to the next one. We said it was at 5/4, which is 1.25. So the length should be 2.5 meters. And if we run it here, sure enough, I get a standing wave occurring inside my tube with a node at the fixed end and an antinode at the open end. Now there's the next one. If we follow the same pattern, we're getting odd multiples of a quarter. So we had 1, 3, 5. So the next one should be at 7/4. So if we go ahead and increase the length of our tube to 3.5 meters, we should notice that we get the next resonant length. And so if I'll change this to straight 3.5, and you notice that if we run this, we get a standing wave that occurs exactly there. So we had at 1.75 lambda, which is 7/4 lambda. All right, so let's go back to our note and summarize this as a general equation that can give us the resonant lengths of any of these tubes if we know what the wavelength is. So both in our drawings and in that simulation, we saw that resonant lengths occurred at 1/4 lambda, 3/4 lambda, 5/4 lambda, and 7/4 lambda. So this continues on and on and on. So there must be a general equation that demonstrates this. And in fact, the general equation can be represented by this yellow highlighted equation, where we have 2n minus 1 divided by 4 multiplied by lambda. And n will be our harmonic number. And you'll notice that the difference between these two, between two adjacent harmonics, was essentially just half a wavelength. So you saw here was an addition of half a wavelength, and then this was another addition of half a wavelength. And that is shown in our equation here. And it's also written on the right-hand side of our page here, right? So if we increase the length of our tube by a half wavelength, we get to that next resonant length. Okay, so another thing I could do is I could keep the length of the tube fixed, but change the frequency. And so on our page right now, I've drawn the first 3 harmonics. So the first, third, and fifth harmonics of our tube. And so what we're looking for is that antinode to occur right at the tops or the open part of the tube. And we have a node occurring right at the fixed end of the tube, right? And so what you'll notice is the length of this first tube. So the length here is equal to 1/4 lambda. And I'm going to call that lambda naught as our fundamental frequency or fundamental wavelength. And so the next one occurs at, again, here's our quarter, but I've added in that extra half wavelength. So again, we should get that lambda, or the length, is equal to 3/4 of lambda. And then the last one here, if we have, there's our quarter, and we had a full wavelength, same thing that we found earlier by changing the lengths of them, that the length of this tube would be 5/4 lambda. Now, what happens to our frequency? So you'll notice that the frequency is changing as well. So if we look at the very first one, and I say that our fundamental frequency is given by V is equal to F naught lambda naught. And the naughts just represent the fundamental. The speed of the wave is not going to change on us. So I can say that the speed divided by lambda naught is equal to our fundamental frequency. Well, we know that the fundamental frequency, coming off of this equation here, I can rearrange and say 4L is equal to lambda naught. So instead of writing this equation here on the left-hand side, I can write V divided by 4L is equal to my fundamental. And so I'm going to use that equation here. And what I'm trying to show you is that the fundamental frequency, if I were to triple that frequency, I would get a standing wave inside that middle tube. And so let's analyze that a bit further. From this equation here, I can actually say that that wavelength is equal to 4/3 the length of my tube. And so use the idea again that the speed of the wave is not going to change. The frequency here is going to be V is equal to F times lambda, which means that V divided by lambda, and we're looking at this middle tube, is equal to this frequency. Well, V, again, is just going to be V. The length of it is 4/3 L. Well, rearrange this equation and it will give you 3V divided by 4L is equal to F. Well, if you stare at that long enough, you'll realize that that is just simply 3 times V divided by 4L, which we defined as our fundamental frequency here on the left-hand side of our page. So this tells us that 3 times the fundamental frequency is the frequency that causes the standing wave to occur in that fixed length tube. So if I wanted to go from one standing wave at this location here to the second standing wave inside my tube, I actually have to increase the frequency by 3. So it's the third harmonic there. And if you did the same analysis for the last one here, you'll find out that it is 5 times that fundamental frequency. So it's the 5th harmonic, right? So summarize what we found here. Well, we said that the wavelength for the first tube was 4 times the length of our tube. The next one would be 4 times the length, or 4/3 the length. And the next wavelength that would fit inside here would be 4 times the length of the tube divided by 5, or 4/5 the length of the tube. And the next one would be that the wavelength would be 4L divided by 7, or 4/7 the length of the tube. And this corresponded with frequencies that were in the 3rd harmonic, the 5th harmonic, the 7th harmonic, and so on and so on. So one thing that you're noticing here is that you will never ever get an even harmonic fitting inside this tube that's fixed at one end. It's always going to be odd harmonics. So the first one, then the third one, then the 5th, the 7th, the 9th, and so on. So this concludes our discussion about air columns that are fixed at one end. So we're going to move on to talking about air columns that are open at both ends. And just like our fixed at one end acted like a fixed end of a string or a spring, and so if you sent the pulse down that string, it reflected back at the end. Well, open air columns act like both ends are free to move. So we should see antinodes at both ends of our tube, if in fact it is at a resonant length. And so if we wanted to draw the first couple here, you would see that I want an antinode at both ends. And I'm going to have then have a node occurring at the middle. And I can have the same thing occurring in each of my tubes. So if I increase the length of my tube, the only thing that is changing here is the fact that my wavelength is increasing, which means that the frequency is decreasing. And what I'm hoping that you're noticing here is that as this length of the tube increases, the wavelength is also increasing. But the length of my tube is always going to be half a wavelength in this case here. So you'll see that I went from an antinode to an antinode. That length is in fact 1/2 wavelength, and this one was also a half wavelength, and this one was also a half wavelength. So we notice that since the speed is fixed, if the wavelength increases, the frequency had to decrease. And this explains why a trombone, that instrument that decreases its frequency or its pitch as the air column gets longer and longer. Okay? So just like we did with our air columns that were fixed at one end, we're going to investigate how we can change the length to create harmonics and how we can change the frequency to create these harmonics. So let's first investigate if I keep the frequency constant but change the length. So the frequency, my fundamental frequency that I'll deal with here is this frequency right here. And I'll draw my reflected one in as the dotted. So I have my node in the middle and my antinodes at the ends. Okay, so for the next one, if I wanted to increase that length, I still have the same frequency, which means that the distance between my nodes and my antinodes will remain the constant here. So this is my incident and here's my reflected. But I want to have the next fundamental length. So the resonant length here will then have a node and then an antinode. So because the frequency stays the same, the distance between my nodes and antinodes must remain constant as well. So what you're noticing here is that the next resonant length is the addition of yet another half wavelength. So the first one occurred at half a wavelength. So the length here was lambda by 2. This one occurred at 2 of those lambda by 2s, which means that my length was lambda. And the next one would be 3 lambda by 2, and that was drawn here. Let's draw it as there's my node, my antinode. It comes in, it does this. This is my reflected back. And then the next one was blue, so I'm going to draw this one in as my node, my antinode, and it comes down like that. And here's the reflected one coming back. And then the next one I'll do in, I guess, green. And we'll have our node, and it comes down. Oops, that's supposed to be the reflected one. So there's our dotted coming back as the antinode and the node. And then this is our solid incident wave coming back the other way. So you can see that I have a half, another half, and then yet another half. So the length of this tube here is 3/2 my wavelength. Okay, so these resonant lengths occur at half multiples of these half wavelengths. So n represents that harmonic number, so this would be the third one. And so you get that the third resonant length is at 3/2 lambda. Okay, so let's fix the length of our tube and change the frequencies. So let's fix this length here and look at the first harmonic. So the first harmonic occurs when I have an antinode, a node, and an antinode. And we knew that from our above discussions. And then the reflected one comes back and I get this situation here. Okay, so if we look at that situation, we get that the length of this tube, and we said that above, was that it was 1/2 of lambda. And then the frequency would be F0. Okay, so the next one, if I wanted to keep the length the same, the frequency has to double because I have to get 2 of these half wavelengths inside my tube. And I'll correct the bottom half here. This part here should be my dotted. And you'll notice that the 2 of my wavelengths have now fit inside there, or 2 of my half wavelengths. So L is equal to lambda, or we get twice that fundamental frequency. So you can see that I have to double my frequency because I need twice as much to fit inside that tube. And so the next one, if I have my node, and my node, and each of these is a half wavelength, so I'm drawing it coming down, and my reflected coming back, antinode going into the node, antinode going into the node, and antinode coming back. This we said was the length of 3 halves. Sorry, 3 halves. Lambda, this is just simply 3 times that fundamental frequency. And this is all because the speed of my wave does not change. And so if the frequency is going to stay, sorry, if the length is going to stay the same, then my frequency has to change based off of how my wavelength is changing. Okay, so let's look at a couple sample problems that deal with these open and closed tubes. Okay, so before we get going, this was our first harmonic. This was our second harmonic. And this was our third harmonic. And you'll notice that we are actually getting every single harmonic, both even and odd harmonics, not just the odd ones like you saw in the closed end of our air columns. Okay, so let's actually go ahead with those problems now. So in the first problem, we have a resonance box, just like the one I showed you at the very beginning of this video, and it's resonating at 256 hertz. So we know that the frequency is 256 hertz, and we know that the temperature is 20 degrees Celsius. That temperature allows us to find the speed of sound. So if we remember that the speed of sound is equal to 322 meters a second plus this conversion constant of 0.59 meters per second per degree Celsius multiplied by the temperature, we can find out that the speed of sound will give us an answer. Let's actually do the calculation. 322 meters per second plus 0.59 meters per second multiplied by 20 degrees Celsius divided by degrees Celsius. Here we go. And we find that the speed of sound is 343.8 meters per second. So if we were going to use this resonance tube, and if we were hearing that loud point, we know that the openings are antinodes, and the fixed end, or the back of the box, has to be a node. And so if we draw in our wave, we get something that looks like this. And so the incident wave is actually going to be 1/4 of the wavelength itself. So if we can determine what the wavelength is, we know the length of the box. And so let's go ahead and determine the wavelength. So V is equal to the frequency multiplied by the wavelength. So the velocity of the wave, or the speed of the wave, sorry, divided by the wavelength is equal to that frequency. And so we know that we have 343.8 meters per second divided by this, let's actually calculate the wavelength, not the frequency. So the frequency here, 256 hertz as our wavelength, and we get a wavelength of 1.34 meters as lambda. Okay, so we're going to use that lambda to find the length of our box. So the length of our box is given as 1/4 of this wavelength. So L of 1/4 multiplied by 1.34 meters, and we get an answer of 0.335 meters, or the length of the box is 33.5 centimeters. Okay, so that tells us the length of this box. The second problem, the male vocal tract, so the length of it is 21 centimeters, which is 0.21 meters. And it acts like an air column closed at one end. So let's go ahead and draw what that looks like. So we have an air column, and I'll actually use a ruler. So I have my air column here, and it's closed at one end. And we have the speed of sound told to us. So the speed of sound is 348 meters per second. and it's vibrating in its third harmonic. We want to know what the wavelength of the sound is and what its frequency is. Okay, so if it's in its third harmonic, we know that it has to have antinodes at the opening. It has to have a node in at the fixed end, and it has to have a node along the path. So I have this situation occurring right here. So I have that we have the antinode going to a node, that node coming through to an antinode back to a node, and then the reflected wave coming back the other way. So this is our third harmonic. In that third harmonic, the length of that air column would then be 3/4 lambda, based off of our diagram there. So if I know the length of the tube, which I do, I can find the wavelength. So we have 0.21 meters is equal to 3/4 the wavelength. Solving for the wavelength, you get an answer of 0.28 meters as lambda. So we know the speed and we know the wavelength. That allows us to find frequency now. So V is equal to F times lambda. So F will be V divided by lambda. So F is equal to 348 meters a second divided by this 0.28 meters, which gives us a frequency of about 1,243 hertz. And so I've gone ahead, we found the wavelength of the wave that fit inside the male vocal tract, and we found the frequency of the sound that fits exactly inside this vocal tract as well to produce that third harmonic. So the third question that we're going to deal with is that we want to know what the frequency of a tuning fork is if it has an open, if it's resonating inside an open tube. So the open tube looks like this. The temperature is 20 degrees Celsius, and it's sitting in the third harmonic. So the third harmonic for an open tube looks like this. So it has to be antinodes at both ends, and it has to have a node here and here. So we go from antinodes to nodes to antinodes to nodes, and then back into antinodes. So that's what the one looks like, and this is the reflected. And I'm just going to fix this wave here. There it is. All right, so from before we can find the speed of sound. So 322 meters a second plus 0.59 meters per second per degree Celsius multiplied by the temperature, speed of sound. If we insert that 20 degrees Celsius, here we go, 20 degrees Celsius, we find that the speed of sound again is 343.8 meters per second. And if we know the length of this tube, we do. The length is 0.52 meters or 52 centimeters. Then we can find the wavelength. So we remember that the wavelength here in this tube will be 3/2 that wavelength equal to the length. So we have 0.52 meters is equal to 3/2 the wavelength, which means that our wavelength gives us a value of 0.346 meters when you isolate for lambda. So we now have the wavelength, we have the speed. Let's go ahead and determine the frequency. So if we remember that V is equal to F lambda, you have that 343.8 meters a second is equal to F times 0.346 meters, which gives us a frequency of 994 hertz. So there we go. We were asked to find the frequency of the wave that is in a air column that is open at both ends. So in this lesson, we looked at air columns that were fixed at one end as well as air columns that were open at one end. If you have any questions or concerns, please don't hesitate to reach out to me.